let's look at rational functions and how they can be graphed. So a rational expression is just the quotient of two polynomials. So it's basically a fraction with a polynomial on the top and a polynomial on the bottom. And if the denominator was equal to 0, then of course the rational function would be undefined. And so any value of x that gives us a 0 denominator is going to be something that actually is not included in the domain, because the function will be undefined at that point. So in example A, it says find the domain of this rational expression. And so we'll do this with by factoring the top and the bottom, and we end up then with it doesn't actually really matter if we factor the top if all we're looking for is the domain. It's really the bottom that we care about, because if the bottom is equal to 0, then we need to worry about it, because that would be an undefined expression. So clearly, if x plus 5 is equal to 0, then, well, we don't want x plus 5 to equal 0, because that would create a 0 denominator. Similarly, we don't want x plus 4 to equal 0, because that would give me a 0 denominator. And therefore, then, we can say that x is any real number, but, or I can put the line here, however, x is not equal to negative 5, and x is not equal to negative 4. So all real numbers except for those two amounts. And if you're looking at this thinking, well, can't you just cancel the x plus 5 and the x plus 5? You can, in order to be able to find other information about your graph, like asymptotes and intercepts and so on. But if these x plus 5s weren't here, well, then we'd have started with a completely different rational expression. And I suppose x could then equal negative 5. But clearly, when you look at your original expression, if you substituted x equals negative 5 in, you'd get a 0 in the bottom. So we can't just cancel it and pretend that they weren't even there. In fact, we'll see later on this lesson that this repeated factor in the top and the bottom creates something known as a hole in the graph, just a temporary discontinuity that we would graph an open circle at. Now, in order to graph a rational function, which is a fraction between two different polynomials, we'll want to factor the numerator and factor the denominator, and that will help us identify 6 possible key features. I should mention that only one of these last two features can happen at once. So the graph will either have a horizontal asymptote or it will have a slant asymptote. Alright, but we'll look at that later. Let's talk about how to find each of these different pieces of information. We know that to find the y-intercept, we make x equal to 0. Alright, you've had some practice with that, so it shouldn't be a problem. I will just mention that if the rational function is given in standard form, meaning that the numerator is a expanded polynomial simplified with no parentheses, well then and the same with the denominator, then every term in the top and the bottom with an x in it would revert to 0. And the only expressions you'd be left with on the top and the bottom are the constants at the end. And so the y-intercept then would become the quotient of those constant terms. As I was mentioning before, a hole is a type of discontinuity, and holes will occur when we have a factor in both the numerator and the denominator. And so we can find out what the x-coordinate of the holes are by setting that repeated factor on the top and the bottom, like we had in the first example, this x plus 5. This repeated factor would create a hole. If x plus 5 was equal to 0, then we would have a hole where x is equal to negative 5. The corresponding y-coordinate